So previously we've looked at some simple ways to solve differential equations numerically, specifically first order ordinary differential equations. We're going to get a little deeper now and look at sort of the standard bread and butter way to solve these equations. It's a little more complicated, but it's a lot more accurate. In other words, we need relatively few function evaluations in order to calculate the value of the function whose differential equation we're given. This particular method is the Runge-Kutta fourth order method. There's actually a family of Runge-Kutta fourth order methods. They all come from writing out the Taylor series expansion with the Runge-Kutta formula and solving for the constraints. There's a number of possible formulas we could write out. This is the one that people generally use when they talk about a Runge-Kutta fourth order algorithm because it's particularly simple to write out. The constants are relatively easy to remember. So we're going to start out with our definition of our differential equation that we're trying to solve. We have dx dt is some function of x and t, and we have an initial point. We have some initial time, or whatever our dependent function is, at which we know the value of our function. So we've got that, and what we want to do is solve for x as a function of t for all t. And what we're going to do is find a way to figure out what x is at some value of t0 plus delta t, because if we can do that, then we can keep repeating that on and on until we have a function for a function x of t at all time t. So all the Runge-Kutta formulas are of this form. X at t plus delta t is equal to x at the current value of t plus some interval delta t and the average slope over that interval. And that's where the difference comes in. Different Runge-Kutta methods have different ways of calculating this slope. This particular version that we're going to look at, the average slope is calculated as 1/6 of 4 slopes. It's fourth order, and to get it to fourth order you can show that you need to evaluate the function, i.e. the function f of x of t, which is dx dt, in 4 places. And then you weight that average. So in this case, we take the slope at the first point, twice the slope at the second point, twice the slope at the third point, plus the slope at the fourth point, and then we divide by 6 to average it out. You can tell that it's 6 because we have 1 plus 2 plus 2 plus 1 total slopes to look at. That adds to 6. So if we want to have something that's the same order of magnitude as the slope, we're going to divide by the sum of the weights, which is 6. So we divide by 6. And that's our average slope. So that part's pretty easy to memorize. You just remember the 2 in the middle are doubled, and then you have to divide by 6. Now the next question is, at what points x and t do we evaluate these 4 different derivatives? So let's get started. Let's see how you can remember that. Well, we start out at our initial time, t0, and that's the time at which we know what the value of x is. So we have that point. We want to find x as a function of all t. We start out with only 1 t. So the first thing we do is clearly this is the only point we know. This is the point we have to start out with when we calculate our derivative. So that's our k1. It's the function evaluated at x0 and t0, in other words, dx dt evaluated at that point. So if we know the slope of the function at that point, or rather we know the slope of the function exactly at that point, it's an approximation to the derivative of the function over the next time period. What we're going to do to get the next point is go forward a half step, delta t over 2, assuming that the function is roughly linear over that time step, and calculate an estimate for the function at t0 plus delta t over 2. It's not a perfect value of the function because we're assuming it's linear, but it's, a good estimate. So that's our first estimate for the function. And so now we want to calculate the derivative of the function at that point. Well, that's simple enough. We just take x, which is x0 plus delta d over 2 times k1 for our x, and then for our t value it's t0 plus delta d over 2. So we calculate our derivative of the function evaluated at that point. So that's our second slope. Now what we do, this should be a better estimate of the slope at the midpoint than the value of the slope at the first point of the interval is. So now we go from that point over and we take a half step using our second slope. So now we have a third point, and that third point is just going to be x0 plus k2 delta t over 2. And that's the value of x, and the value of t is, of course, t0 plus delta t over 2. And we can calculate our slope there, or in other words, the derivative of the function evaluated at that point, and that gives us a new estimate for the derivative at the midpoint. So then we take that estimate of the slope, the estimate of the derivative of the function, go back to our first point and take a full step. So we take a full step over for the full delta t interval and get a point there. So that gives us our fourth estimated point for the function. And we can calculate our slope at that fourth point. The fourth point, which is x0 plus k3 delta t, a full delta t now, not just half a step. And then the t value is t0 plus delta t. So that gives us our fourth slope, our fourth value of the derivative of the function at 4 different estimated points. Now, for a real function, these would all be much closer together. If we want to have a good estimate of the slope, we have to have a very small delta t, or else the function would change too much. So for a real function, this would clearly be a delta t that was too big, because the derivative is changing drastically over the course of the time step. But we're exaggerating everything, so you can see the differences in the slopes at the different points better. So that gives us the information we need. Okay, so now we can go through and we can see the average slope is 1/6 of 1 times the first slope plus 2 times the second slope plus 2 times the third slope plus the fourth slope. We add those together. So what does that mean? What does it mean, we're adding together a line? Well, really each line is just the value of the slope. It's just a number. And so numerically, well, let's see, the first one looks about 1.2, the second one maybe 0.5, third one is flatter, so maybe 0.3, and the last one is it's higher than the first one, so we'll call it 2. We're just estimating here. So we average those together, and that would give us a slope of about 0.8. So then, now we've computed the average slope. Now we can make the full step and give us our Runge-Kutta estimate of what the value of the function is at t0 plus delta t. So that's our slope. It's going to be somewhat intermediate between all of those. We're averaging all those slopes. So we take that slope and go over a full time step. That gives us our final value of x at t0 plus delta t. That is the fourth order Runge-Kutta, or at least this particular example of fourth order Runge-Kutta. Let's now, we're going to just minimize that little window over in the corner so we can be remembering that as we go through and plug in the numbers for this. So again, remember, this is what we're doing. We're computing an average slope, multiplying that by delta t, and taking and incrementing our current value with that average slope. Our particular average slope here is 1/6 times k1 plus 2k2 plus 2k3 plus k4. And let's use the same function we used for our lower order solution algorithms. It's 3 times x to the 1/3 plus t cubed. So this is a function of both x and t. And of course, we need to have a time step size. So we'll choose 0.1. And we need to have an initial point. So we're going to start at t 0.2, and we're going to assume that it's 0.1. Now, these numbers do not necessarily correspond directly to the numbers on the graph. Don't try to look at the graph and get the numbers to fit exactly. In order to fit everything on the graph, I had to choose a bit of a different scaling for that. So just use the figure as a reference to remember what goes where, not to actually look up what the value of the slope is or the function is at any given point. That's just to give you a sense of what order the function values are. Okay, so now our first slope in red, we evaluate from the first point. So we go through, we plug in x of 0.2, that's our initial point, and t equals 0.2. Well, x of 0.2 is just 0.1, so we plug that in for x, and we get a slope of 0.95668. Great, that's our first slope. So now we're going to calculate the value of the function at t plus delta t over 2. Delta t is 0.1, so delta t over 2 is 0.05. So now we're interested in the value of the function at 0.25, and so that's x of 0.2 plus k1 times delta t over 2, and we get our first estimate of x1 at t equals 0.25, which is 0.41784. Okay, so now we can figure out the value of the slope, that's the light blue line, at that point. We just plug in the numbers. We can plug it in using the formula we're given. We get an estimate of slope is about 1.16912. That's not that far from 0.95688, so we probably get a decent time step. The slope isn't changing a huge amount. Okay, so now we can figure out our second guess for the value of the function at the midpoint. And so we take the initial value plus k2 delta t over 2, plug that in, we get a new value of the function. And from that we can figure out the slope at that new estimate of the function x at the midpoint 0.25. Plug it in, we get a new slope, it's 1.20982. The slopes aren't changing very much, so that's good. We've got a decent estimate. And then finally we take a full time step. We have the value at 0.02 plus k3, the orange-yellow slope, times delta t. We make our full time step, and we get a value of 0.22098. Okay, great. And we can calculate the slope at that point. Plug in all our numbers, and we get a slope of 1.43726. Sounds reasonable. Slope hasn't changed too much. So we've got our four slopes, and now we just average them together, and we get an average slope over the entire interval delta t of 1.19170. So as we see, that's intermediate between all these different values, so that seems like could be a pretty good estimate. It doesn't look like we're taking too big a time step. And so our final answer, now we've got an average slope, it's pretty easy. We just say it's going to be x at t0, which we know, plus the average slope times delta t, plug that in. This math is easy. We're just plugging that in, and we get a value of 0.21917. Is that good? Well, what we can do is actually go through and use ODE 4.5, set a really tight tolerance. In this case, I've set the tolerance down to 10 to the minus 9, so it's a very accurate answer. We get the true answer as 0.219257. So we got very close to that true answer using just one time step and 4 function evaluations. So if we look at that, we're within 0.04% of the true answer with just one time step over that period. So it's a very accurate method for most differential equations. You could come up with stiff differential equations or some other sort of quirky cases, which do come up from time to time, where you want to try something else. But this ends up working very efficiently in most cases. So that is our summary of a particular example, the most common example, the one that's sort of the default that you try, of fourth order Runge-Kutta algorithms to calculate numerical solutions to first order ordinary differential equations.